All right, so we spent the first part of this chapter talking about the differences between alkenes, alkynes, and the alkanes that we already learned about in the previous chapter. Then we've just discussed the cis and trans isomerism that is the hallmark of alkenes. It doesn't have to happen in every alkene, but it is something we certainly consider when we see an alkene. And now we're going to move into some further differences between the alkenes, alkynes, and alkanes, right? The alkanes we didn't have to worry about cis-trans. We also didn't have to worry about too much in the way of reactivity. And here we'll see that there's some reaction types that we can expect alkenes and alkynes to experience that alkanes did not. So specifically in this lecture, we're going to discuss addition reactions, and these are reactions that occur when you have an unsaturation, like a double or triple bond, that again you can't have with fully saturated alkane. So these are addition reactions that tend to characterize the alkenes and alkynes and make them distinct from the alkanes we've already talked about. All right, so in an addition reaction, we have reactants add to the carbon atoms in a double or a triple bond. So that it's a little misleading here on the slide where it says a double or triple bond is easily broken. That's not necessarily true, right? They're pretty short and pretty strong, especially triple bonds. But in the right set of conditions with the right reactants, we can overcome the energy necessary to break that double or triple bond in order to add. So we can indeed break the bonds. I don't think easily broken is necessarily what you think of as easily broken is what we mean by this. So we mean compared to a single bond, which is quite stable and not prone to addition reactions, double and triple bonds are much more readily able to engage in this addition process. The double bond is a source of electrons for these new bonds. So if we look at our generic alkene, which is that carbon-carbon double bond, and some generic reactant, AB, in an addition reaction, we'll have A add to one carbon of the double bond and B add to the other. And now notice our product is no longer an alkene, but rather an alkane. Everything's saturated. We have no more multiple bonding in this example. Here in table 12.2, we have a summary of different addition reactions that we might encounter. So hydrogenation, we've already talked about, and we even mentioned the partially hydrogenated vegetable oils that used to be much more common in foods before we had to declare those trans fats, which are often a result of partial hydrogenation. So in this case, we can take an alkene. If it has just one double bond in the alkene, then every mole of that alkene can react with 1 mole of hydrogen, typically on a platinum, nickel, or palladium catalyst, right? That special family there in the transition metals that just happen to hold these alkenes in just the right position for hydrogenation, and we get it fully hydrogenated to an alkane. Likewise, if we have an alkyne, a triple bond, if there's one triple bond in the alkyne and we add 2 moles of hydrogen, right, the first mole of hydrogen would reduce the triple bond to a double bond, and then that second mole of hydrogen would reduce that double bond all the way down to single bonds, same sort of platinum, nickel, or palladium catalyst, same alkane product. Again, that's fully hydrogenated. If we did partially hydrogenated, as I mentioned, either we didn't add enough hydrogen to have a 1 mole hydrogen, 1 mole alkene ratio, or we only added 1 mole to an alkyne, we might end up with still some unsaturations. But to keep things simple, we're going to imagine everything goes to completion. We're fully hydrogenating to get alkanes from these alkene or alkyne reactants. For halogenation, instead of hydrogen, we're adding a halogen, whether it's chlorine, bromine, fluorine, iodine, right? It could be any of those options. For an alkene, if we add a mole of chlorine to an alkene that has just one double bond, well, the chlorines will add 1 to 1 carbon of the double bond, 1 to the other, and we'll get a haloalkane. Likewise, for an alkyne, now because we have a triple bond, we'd need 2 moles of chlorine for every mole of CC triple bond, or 2 moles of bromine or fluorine or whatever the halogen might be, to get it reduced all the way to a haloalkane. Right? If we had just 1 mole with an alkyne, we might get a haloalkene. And finally, for hydrohalogenation, we can have an alkene and a gas like hydrogen chloride or hydrogen bromide, these wouldn't be hydrochloric acid or hydrobromic acid, right? Because we wouldn't be in water here. Alkenes don't like water. They don't mix well with water. So we'd be dealing with the gas phase, hydrogen chloride or hydrogen bromide reactant, and then we'd get a haloalkane. And one position of the double bond, we'd get the hydrogen added. In the other position of the double bond, we'd get the chloro group added, or the bromo group, or the iodo group, or fluoro group, whatever the case may be. Finally, for hydration, we can take alkenes and water. This would be water vapor, because as I just mentioned, the alkenes don't mix well with liquid water. If we had a strong acid catalyst, we could make an alcohol, right? Just like the hydrohalogenation has a hydrogen add to one carbon of the double bond and a chloro group add to the other. In this case, we'd have a hydrogen add to one carbon of the double bond and an OH, a hydroxyl group, add to the other, and that would make us an alcohol. And again, this could be done in the water liquid phase if we had a strong acid and if we had some sort of phase transfer catalyst going on. So there we have it, a summary of addition reactions. All right, so taking a chance to just look at select examples of those one by one. If we look at hydrogenation and we look at the hydrogen atoms adding to the double bond or triple bond carbons, again, we would need some sort of catalyst. It's not critical in this course that you necessarily know whether it's platinum or palladium or nickel, because they'd all give essentially the same product for our purposes, but you would need to know that there's some sort of catalyst present, and I would often provide that for you in the text if I were to ask about a problem. So we have an example here with an alkene hydrogenating to form an alkane, so generically, and then specifically if we're looking at 2-butene, and again, because it is 2-butene, we could discuss cis or trans isomers, right? It wouldn't matter here for our product, but ultimately we could start with cis-butene, trans-butene, or a mix of cis and trans 2-butenes, and then hydrogenate them. And at the end of the day, with our platinum catalyst, we'd end up with good old butane. No need to worry about cis or trans there. So as I've mentioned already, hydrogenation of oils was one of the major applications of this adding of hydrogen to double bonds. The reason it was done was to make margarine, to make a butter replacement, right? We were looking for something that acted like butter, but was longer lived and didn't rely on necessarily cows and cow's milk and all of those things. So it was discovered in France that you could hydrogenate these vegetable oils and you'd get more solid type substances rather than the liquid vegetable oil itself. So they tend to be solids at room temperature, such as margarine, soft margarine, shortening, and really shortening can't be replaced, right? Margarine you could replace with butter if you're trying to cut trans fats, but shortening there's no perfect replacement for. So if you really like things that are made with shortening, the shortening still has trans fat. You can read the label. Crisco still has trans fat in it. But if it's something that you really can't live without, I guess it's worth the risk that that trans fat might cause some cardiac issues down the road. Okay, so now that we've looked at a hydrogenation example together, let's have you go ahead and try your own. So this learning check asks you to write an equation for the hydrogenation of 1-butene using a platinum catalyst. So please pause the video here, complete that task, and start us back up when you're ready to check your work. Okay, so I was kind here because it's 1-butene. You don't have to worry about cis or trans. And if I don't specify, like in the case of the 2-butene that we looked at before, you can just assume it's some mix of cis and trans. But if I do specify, then obviously I would need to see a specific type in your chemical reaction. So here, 1-butene can't have cis-trans isomers because the carbon 1 of the double bond has the same group as its two components. So they're both single bonds to hydrogen. So we'll either do the condensed structural formula as you see here, or preferably the Skaldo formula if you've already gotten used to those and like to use those instead, then certainly send it to me if you're not sure if it's right, but hopefully it would look just like this, but the correct Skaldo formula. So we have our 1-butene represented. We have the plus sign to indicate that we have a co-reactant of H2, and then over the arrow, because we specified a platinum catalyst, you would have platinum's chemical symbol, capital P, lowercase t, and then the product of this hydrogenation is just plain old butane. So hopefully that's where you ended up, and if either you're not sure if you got it right or you didn't get it right and you're not sure why, please go ahead, reach out to me. I can certainly give you some advice and either confirm that you did indeed get it right, or give you some additional problems if you're having trouble with this concept. Let's try one more learning check on this, and here we do get to see a Skaldo structure down there at the bottom. In this learning check, you're going to draw the condensed structural formula of the product of each of the following reactions. So we've given you the reactants, we've given you the catalyst. Your job here is to draw the product. So please pause the video here while you do that, and once you're ready to check your work, please start us back up and we'll see how you did. Okay, nice and easy, right? Hydrogenation reactions are your friends here. They're not very tricky, and what you see is what you get. So we're just taking that double bond in our first case in that condensed structural formula, and we're taking the double bond there and reducing it to single bond. So that means it's just going to be a single bond between carbon 2 and 3, and therefore we need one more hydrogen to give each of those carbons 4 bonds total. Those hydrogens, of course, came from the H2 that was the co-reactant. In the case of our cyclopentene and hydrogen, when we reduce it, we get cyclopentane. So we're just taking away that double bond by reducing it to single bonds through the use of hydrogen. So again, hopefully this went well for you as well, but just a little more practice with the idea of hydrogenation reactions. Okay, halogenation, again, not much different from hydrogenation. We're just changing the elements involved here. So in a halogenation reaction, we use halogen atoms, such as chlorine or bromine, instead of the hydrogen from hydrogenation, to have those add to the carbon atoms of a double or triple bond. Obviously, they also will reduce the double bond in this case to single bonds, but instead of a plain old alkane like we got for hydrogenation, we're now going to get a dihaloalkane if we reduce an alkene by halogenation. Now the halogens are a very reactive family. Hopefully you remember that from General Organic Biochemistry 1. Halogenation reactions of alkenes or alkynes typically occur quite rapidly without the need for a catalyst. So the hydrogenation reactions required platinum or palladium or nickel catalysts. Here we don't need that. We don't need any catalyst at all because the halogen itself is reactive enough to add to the double bond without the need for catalysts. So in the top case we have ethene rather, right? It's a double bond, so ENE ending, shame on me. And the ethene and bromine react to form dibromoethane, right? Technically 1,2-dibromoethane if you want to name that thing. Below, now we have a triple bond, so we have a propyne, and propyne therefore requires 2 moles of chlorine to fully halogenate, and in this case, ultimately, if we fully halogenate that propyne, we get 1,1,2,2 tetrachloropropane. So there we have it. A little bit more exotic of a name than maybe we've gone through so far, but not too bad. It still follows all the rules, right? And hopefully it's something that now that I say the name, you would have been able to come up with that on your own. Now, because bromine is an intensely colored liquid, and because double bonds or triple bonds are quite reactive with bromine without the need for any catalyst, bromine is often added to test for unsaturations. When you add bromine to an alkane, the red color of the bromine persists, because without special conditions, typically light, you can use certain wavelengths of light will help promote the bromine to react with a halogen, the alkane hydrocarbons, the CH bonds, but in the absence of that special light, you don't really see any reaction of bromine with an alkane on a normal time scale. However, if you have alkenes or alkynes present, if you have carbon-carbon double bonds or carbon-carbon triple bonds present in your substance, as soon as you add that bromine, you'll get the red color of the bromine disappearing immediately because it's not remaining as elemental bromine as it did up above with the alkane. Instead, now it's reacting to form brominated halo carbon compounds. Okay, so you can even find what's often called the iodine number. If we use iodine instead of bromine, you can find how many unsaturations you have in something like a fatty acid by using a test like that, just to see how much of that halogen, in that particular case iodine, the sample can take on before it stops reacting, before you get the persistent bromine color in this case, or iodine purple color in the case of the iodine number for fatty acids. So a very useful test to see if you have unsaturations. Really qualitative test here, but it can be a quantitative test too, because once you've fully reacted all the bromine or iodine or whatever the halogen is with the unsaturations, then if you add any more, it will just sit around because everything is now a haloalkane. Let's go ahead and follow up with a learning check. In this case, you're asked to draw the condensed structural formula of the product of each of the following addition reactions. So you've got 2-butene. Again, it would either be cis or trans specifically if we were to use a structural formula that's a little more comprehensive, and definitely if we did a skeletal structure, that's reacting with chlorine gas to form a product that you're going to draw for us, and fortunately that product will no longer be subject to cis-trans isomerism. And then down below you have a cyclohexene that's reacting with bromine, and in this case, if you could, instead of showing the condensed structural formula for this one, if you could show the skeletal structure, it'll be much easier for you. Okay, so pause the video here while you complete those tasks and start us back up when you're ready to check your work. Okay, so for number 1, we just took each of those carbons engaged in the double bond, so carbons 2 and 3 of our 2-butene, and we add a hydrogen. Well, the hydrogen was already there. What I should have said is we add a chlorine to each of those. So now we have carbon-carbon single bonds, still the carbon-hydrogen single bonds, and the double bond is now a carbon-carbon single bond, and we have a carbon-chlorine single bond for each of those carbons that was previously engaged in the double bond. Down below, even easier, right? Because we have that skeletal structure, which is just simplified and easy to deal with. So we take each of those positions on the hexagon there of the cyclohexene, the 2 positions that were engaged in the multiple bond. Now we add a bromo group to each of those carbons to get 1,2-dibromocyclohexane. The name there for the product in number 1, of course, 2,3-dichlorobutane. All right, so hopefully you did well. You weren't asked to name them, but we should always be thinking about nomenclature, because if you don't think about it, it will come back to haunt you. But certainly, as long as you drew the structures correctly and now could name them, you're in very good shape. Okay, so now that we've discussed hydrogenation and halogenation, let's talk about hydrohalogenation. So in hydrohalogenation, we get the atoms of a hydrogen halide, such as HCl or HBr, and again, it's usually the gas that we're dealing with. These add to the carbon atoms of a double bond or a triple bond, also without a catalyst. These are also reactive gases, just like the halogens themselves, and so unlike hydrogen, which did require platinum or palladium or nickel as a catalyst, we don't need a catalyst here to get these reactions to go forward. So we see a generic one for a generic alkene, carbon-carbon double bond, reacting with HX, and the X is a generic letter to denote a halogen. So we get a hydrogen adding to one carbon of the double bond, and the X, the halogen, adding to the other. We see here, again, another 2-butene example where we have hydrogen chloride adding, and we get a hydrogen adding to one of the carbons engaged in the double bond and the chloro group adding to the other. If we look at our cyclopentene, excuse me, if that cyclopentene reacts with a mole of hydrogen bromide, now we add a hydrogen to one position and a bromo group to the other. In these examples, it didn't matter which we put where, but sometimes it does indeed matter where you put the halogen and where you put the hydrogen. Now, our course is an introduction to organic chemistry, so we don't do a whole lot with mechanisms. If you were to take a 200 level organic chemistry, you would probably do much more of this mechanistic organic chemistry, as we call it. But here, for hydrohalogenation, it does occur in 2 steps, and it is worth pointing it out. So as we see, that carbon-carbon double bond is reactive, and we snag the hydrogen off of our hydrogen bromide in this particular reaction in step 1, and we form what's called a carbocation. So carbon likes to make 4 bonds. We've talked about that already, and that's a theme throughout the rest of the course, right? We tend to see 4 bonds to every carbon. But sometimes, temporarily, carbon can stabilize a positive or negative charge, and in this case we have a formal positive charge on the carbocation there, which makes it ideal for that bromide ion, right? When the hydrogen was taken from hydrogen bromide, the bromine kept both of those electrons, so the hydrogen was taken without its electron behind, and therefore the bromine from the hydrogen bromide now becomes the bromide ion. Being a negatively charged ion, it's very attracted to that carbocation's formal positive charge, and therefore in step 2, that bromide ion attacks that carbocation and forms a carbon-bromine bond to form our bromoethane product. Okay, so I mentioned a couple slides ago at the end that in the particular examples that we had shown, it didn't matter where you put the hydrogen and where you put the halogen, but I did say that sometimes it does matter, and now's the time to learn that rule, and it's known as Markovnikov's rule. So in asymmetrical alkenes, the hydrogen in HX, whatever the particular hydrogen halide is, adds to the carbon in the double bond that has the greater number of hydrogen atoms. So if we think back to that mechanism from the previous slide, the carbocation, the carbon, is bearing a full positive charge, and the way that carbon bearing that form of positive charge can have the stability it needs to be a stable carbocation, even on the order of fractions of a second, is to have more alkyl groups around it so that it can have those groups donate some electron density through bonds to stabilize the carbocation, right? It's a positively charged carbon, so it needs that negative electron donation from its neighboring carbon groups. Neighboring carbon groups can stabilize it a lot better than hydrogen. Hydrogen doesn't have a whole lot of electron density to give relative to the carbon groups. So there we see, if we have that unsymmetrical alkene that we start with at the left, we could theoretically make the carbocation with the first carbon of the double bond, but then that has fewer carbon groups attached. It's not going to be as stable. It does not form. Instead, we preferentially form the carbocation where we have that second carbon. In terms of our structure, it would be carbon 2 that forms with the positive formal charge, and then ultimately we go on to form the bromine in that position. So it does matter. It's known as Markovnikov's rule. A simplified way to think about it is those that have get. So the carbon that already has the larger groups on it gets the larger group, and the carbon that has more hydrogens on it gets the hydrogen from the HX. Okay, so however you remember it, whether it's the mechanistic way that it really works, or just that simplified the rich get richer, the poor get poorer idea of whoever has more hydrogens to begin with is going to get the hydrogens, and whoever had fewer hydrogens to begin with is going to get the halide. either way, at the end of the day, I suppose, getting the answer correct is most everyone's goal. And so while I'd love to have you all understand it from a mechanistic standpoint, for our course, we don't do a whole lot of mechanistic organic chemistry. So if you can keep it straight another way and you get it right all the time, then I guess we've both done our jobs. Okay, let's follow up with a learning check to see how well you understand Markovnikov's rule. So in this learning check, you're asked to predict the product for the following reaction of 1-pentene with hydrogen chloride. So if you would go ahead and draw the product, again, there's one product that should form and one product that won't form. So please make sure that you think carefully, try to apply Markovnikov's rule, and draw the product of this reaction. Pause the video here and start us back up when you're ready to check that work. Okay, now notice carbon 1 of the double bond already had 2 hydrogens on it, whereas carbon 2 of the double bond had a hydrogen and a propyl group, and so therefore we would expect carbon 1 to get the hydrogen. It already had more hydrogen, so we expect it to get the other hydrogen. Markovnikov's rule isn't about being fair, it's about the way things work. And then finally, carbon 2, which had fewer hydrogens to begin with, is going to get the chloro group, so that we have the product that we see here. Again, yours might look a little different, especially if you did a skeletal structure as opposed to the condensed structural formula, but as long as you have the correct species in the correct position, then you're in good shape. If you don't have that, if you're having more serious issues, please try some additional problems. Markovnikov's rule does take some time for most people, so you shouldn't feel frustrated if you happen to get this one incorrect. But if you've tried several more and it's still not making sense, please do reach out for some help. Okay, so now in our addition reactions, we've discussed hydrogenation, halogenation, hydrohalogenation, and finally now we're ready for hydration. So in a hydration addition reaction, a strong acid catalyst is required. We get water, HOH, which we can think of as an H and an OH here in organic chemistry, adds across the double bond. So we add an H atom to one carbon in the double bond, and an OH bonds to the other. And so we see here for a generic alkene, we add that water, HOH, in the presence of an acid catalyst. In particular, sulfuric acid is commonly used. We could talk about hydrochloric acid. It's just a strong acid. And we find the hydrogen adds to one carbon that was formerly participating in the double bond, and the OH adds to the other to form an alcohol. And we see here a specific example. There's that darn 2-butene, whether it's cis or trans, we don't really know from that condensed structural formula, but after we add the HOH to it in the presence of an acid catalyst, we end up with an alcohol here, which would be 2-butanol. So we may not know whether we started with cis or trans 2-butene, but we don't really need to know that because either way we end up with the 2-butanol product. Now, just as we discussed for the hydrohalogenation, which also had 2 different substances, right, an H and a halogen, here we have an H and a hydroxyl group. We have to think about how it would add, right? When we had 2 hydrogens in hydrogenation or 2 bromines in bromination, we didn't have to worry about it because it didn't matter which species we put. Since they were identical, we just put a bromine on each carbon or a hydrogen on each carbon that was formerly involved in the double bond. But when we talked about hydrohalogenation, we talked about Markovnikov's rule, and Markovnikov's rule said that the species that starts with more hydrogens of those carbons participating in the double bond would get the hydrogen, and then whoever started with fewer hydrogens would get the non-hydrogen group. And that same Markovnikov's rule that applied for hydrohalogenation also applies for hydration. So if you've got an unequal number of hydrogen atoms, the hydrogen from the water bonds to the carbon in the double carbon-carbon bond that had more hydrogen atoms to begin with, and the OH group, the hydroxyl group, bonds to the carbon in the double bond that had fewer hydrogen atoms to begin with. So just like with hydrohalogenation, we have hydration following Markovnikov's rule. Okay, so since you're already experts on Markovnikov or Markovnikov, sometimes it's shown with a V, sometimes two Fs, and my Russian pronunciation is not very good anyway, so I apologize to anyone who really knows how to pronounce Markovnikov's name, but in this learning check, it doesn't matter how you spell it or say it. If you can apply Markovnikov's rule, then you're in good shape. So here you're asked to draw the condensed structural formula of the product of the following hydration reaction. So we have that hydrocarbon, sort of a quasi-skeletal structure there, reacting with HOH there in the presence of an acid catalyst, and your job is to predict the product. Now there's a product that will actually form and a product that won't form, so your task is to find the product that will form, draw it, and pause the video here while you do that, and start us back up when you're ready to check your work. Okay, so you weren't asked to name this thing at all, but it happens to be a pentene, a 2-pentene to start with, and then if you want to be specific, it's a 2-methyl 2-pentene, and it can't be cis or trans because we have methyl groups coming off of that carbon 2, so we have two identical groups, we can't worry about cis or trans in this case. So since it is a pentene, and since it is a substituted pentene, we happen to have no hydrogens at all on carbon 2, but we do have one hydrogen on carbon 3 of the double bond. So it's a 2-3 double bond. Carbon 2 has its pairings maxed out with methyl groups, whereas carbon 3 has one hydrogen and then an ethyl group, as well as the double bonding partner. So if you follow Markovnikov's rule, well, carbon 3 there had the hydrogen to begin with, which was one more hydrogen than carbon 2 had. So carbon 3 gets the hydrogen from HOH there, water in our hydration reaction, and carbon 2 therefore gets the OH. So we end up with that product there, and I'll save its name until we talk about alcohols in the next chapter. Hopefully that was the product you arrived at. If it was not, if you had the OH and the H switched there, you broke Markovnikov's rule, shame on you. But since you're still getting used to that concept, please do try some additional practice problems. And if you continue to struggle, then certainly reach out to me for help. Okay, so since we talked about 4 different kinds of addition reactions in this chapter, we should probably have at least one more learning check before we leave this lecture. So in this learning check, you're asked to draw the condensed structural formula, or in the last case, the skeletal structure of the product of each of the following reactions. So go ahead and determine what the products for A, B, and C should look like. Draw those in. Pause the video while you do that, and then once you're ready to check your work, start us back up and we'll see how you did. All right, so for A, we had a propene reacting with chlorine to form a 1,2-dichloropropane, and hopefully that was nice and easy for you. The chlorine is an example of a halogenation, and just like hydrogenation, halogenation really doesn't require so much thought because you're just giving each member of the double bond, each of those carbons gets a chloro group. For B, now we do have quite a bit of thought involved with this hydration because we have to consider whether or not we have to worry about Markovnikov's rule. Now, if we look, because it's a 2-butene, whether it's cis or trans wasn't specified, but because it is indeed a 2-butene, we have to be thinking about whether there's somebody who has more hydrogens than the other. Fortunately for you, in this case, they happen to each have one hydrogen. Each of the carbons involved in the double bond has one hydrogen. So when that's the case, and we have actually a symmetrical molecule here, it does not matter which gets the hydrogen and which gets the OH because nobody has more hydrogen to begin with. So you could have shown the structure I show here, or you could have shown it where you had the OH on carbon 2 and the H on carbon 3, because if we flip them around, they're identical, so you didn't have to worry about that here. Finally, for C, because it's a hydrogenation, again, we would need a platinum catalyst or palladium or nickel, and we would get the product. You could either show the H's like I have here just to highlight them, or you could have just had the pentagon for cyclopentane, because of course we don't ordinarily show hydrogens when we have a saturated alkane, even a cycloalkane like this. So hopefully these look like your products and you're doing very well with all of this. If that's not the case, please do try some additional practice. Look at those end of chapter questions. Ask me for help or for more practice problems, and we'll get this down so that you're Markovnikov experts when you need to be, and you're experts with the other types of addition reactions as well. Okay, so we'll meet again in the next part of chapter 12.